Welcome to the final lecture in the series of lectures on data structures. In this video, we'll be discussing the dict data structure. Dict is short for dictionary, and we'll see that the dict data structure in many ways functions like a dictionary for language. But let's first start with a list as our baseline and compare or motivate why we might want a dict data structure. So here we have a list called me, which contains a variety of information about me, my age, my name, my age, something like my height in centimeters and my weight in kilograms, my hair and eye color, and whether or not I have a dog. Now, if we wanted to retrieve information about me for use in a program of some type, then I would have to remember where in the list these various properties are stored. So, for example, I need to remember that my name is in position 0, while my hair color is in position 4. And it's not clear just by looking at the list what these various properties are. For instance, we have 2 browns in this list, and it's not clear which one is eye color and which one is hair color. So it could be very easy to get confused, for instance, about which one is which, and write code that uses the incorrect index. And as soon as someone else's information comes along and they have, say, yellow hair and blue eyes, we might end up saying something like they have blue hair and yellow eyes if we choose the wrong indices here. So instead of referring to the elements of our list by position, it would be very useful to be able to refer to them by name. If somehow in the data structure we could label that this is the name, this is the age, my height in centimeters, my weight, my hair color, my eye color, and whether or not I have a dog. And this is precisely what dictionaries are good for. So, for instance, here I make a dictionary called me dict, and it's created with curly brackets like a set, but instead of just having the values themselves, the data gets entered in as what are called key value pairs. So I have labels or keys that describe what the meaning of the information is stored in the value. So it's my name, that is Dylan. My age is 28. My height is 167.5 centimeters. So this is very convenient because now if we want to, for instance, print out my name and my hair color, instead of remembering these positions, I can access the data using a label. So I can say my name is me dict name. And this way we can ensure, for instance, that when we're entering data, we never put things in the wrong position or forget what position we should look for the information we need, even as the data may change, or we may consider a variety of different data points within a data set. And we can see that this code gives us the same result as before, but is a lot clearer to read. It's obvious that this should print out my name, whereas here it's a little bit mysterious without knowing the order of the elements of the list. So as I said, these labels are called keys, and each key is associated with a value. And together they form what we call a key value pair. And the syntax for creating the dictionary is enclosing key value pairs, which are separated by colons between the key and the value, and the key value pairs are separated by commas. So this looks fairly similar to things we've seen before, but a little bit more complex. At this point, I would ask you to pause the video and consider the two following questions as exercises. When might a dict be more useful than a list? And I would like for you to compare the flexibility of a dict, which contains other dicts, compared to that of a multidimensional array, meaning a list of lists or a list of tuples or something like that. So what might we be able to do with a dict containing dicts compared to lists containing lists? Pause the video, consider these questions, and I'll make a question on the message board where you can respond with your thoughts. Okay, let's continue our discussion about dictionaries. So dictionaries can be created from other data structures by combining them to make key value pairs. So for instance, I might have my list, me, and that would be my list of values, right? That would be Dylan, 28, 167.5, 58 and a half, Brown, true. And then I could also have a list of keys, the labels that I will assign to these values. And if I want to combine these into key value pairs, I can use a function in Python called zip, which will match up each element of these lists based on position. So name will get paired with Dylan, age will get paired with 28, height will get paired with 167.5, and so on. So we'll go ahead and zip together these two lists. Zip returns what's called a generator. I've mentioned generators before, but we're not going to discuss them now. We'll discuss them in the future. But we're going to turn this generator into a list so we can see its contents. So we now have a list of tuples, and each tuple has a key as the first element of the tuple and a value as the second element of a tuple. So these are our key value pairs. I can turn this list of key value pairs into a dictionary by simply wrapping it in the dict type. And now we have that dictionary. Now, dictionaries traditionally are unordered, just like sets. The exact implementation in dictionaries has recently changed in Python, so what I'm about to tell you may be a little bit out of date, but traditionally, or historically, what I'm about to explain has been true, and it's useful to think about dictionaries in the following way, even if they are now technically ordered. So dictionaries also use this hashing technique to store the elements of the dictionary in memory. And the keys are what gets hashed. Therefore, the keys of a dictionary function very similarly to a set. And therefore, the dictionary may not, first of all, cannot be accessed by position. This would refer not to a position, but a key. And we can see there's no 0 key in this dictionary, so we encounter a key error, because there is no key 0 in the dictionary. So we can't access things by position, only by key. Um, and additionally, historically, if I were to print out this dictionary, it would not necessarily appear in the order in which I added elements to it. Something that still is the same is that since the dictionary is based upon hashing, keys must be immutable. If I try to create a dictionary with a list as a key, I get told that lists are not hashable. We need to be able to hash the keys in order to be able to store the key value pair at the appropriate location in memory. However, since tuples are immutable, we can have a tuple as a key. Also, since the values aren't hashed, we are free to have the values be anything we want. So we can have a tuple as a key, and we can have lists as values, but we cannot have lists as keys. Tuples as keys are very useful when we want some kind of compound key, where our key should involve multiple pieces of information. For example, if I had a online store and I had a record of purchases, if I wanted to look at what my customers were buying based on their gender and their country of origin, I might want to create a dictionary where the keys are country and gender, and then for each value I would have a list of all the purchases that people in that country of that gender made. So that's an example of where a compound key might be useful. Dictionaries are also mutable. Here, I can add a new key value pair by simply accessing the dictionary at a new key and then assigning a value for that key. This assignment resembles when we've mutated elements of a list. Dictionaries also have an update method similar to the set. So we can update a dictionary with another dictionary of key value pairs. And we see that now, in addition to my favorite book, I've now added my favorite color, the number of siblings I have, and the number of nieces and nephews I have. And actually, recently, my brother had another son, and so I now have 4 nieces and nephews. We can also delete or replace key value pairs. So, well, I just did that. If my brother were to have another child, this would become 5. So we can see we can change or reassign values within the dictionary. And we can also delete, again, using the del keyword, just like we did for lists. So now there's no longer an entry for my favorite book. Also, as with lists and sets, we can pop elements from the dictionary using their key. So the number of siblings I have is 3, and by popping the number of siblings I have out of the dictionary, we can see the dictionary no longer contains an entry keyed by siblings. Since dictionaries use hashing on the keys, it's very fast to look up data from a dictionary. So dictionaries are often referred to as lookup tables or hash tables. One example of where such a thing could be useful is I might have, for instance, a lookup table for the squares of various numbers. And so on. if I have constructed a lookup table like this, it can save me time calculating results. Instead of calculating the square of these numbers over and over again, I can simply look up the answer that I've already calculated. We'll make use of this in a future discussion on algorithms for a technique known as memoization, where as our algorithm proceeds and we calculate results, we can store them in a dictionary or a lookup table to reference later to save computation time for potentially expensive computations. I can also access the various bits of a dictionary using the various methods of a dictionary for retrieving keys, values, and key-value pairs, which are accessible with the items method. These each return special data structures that kind of combine the properties of sets and lists. So we have a dict keys data structure, a dict values data structure, a dict items data structure. I'm not going to get into exactly what these are. For the most part, you can think of them as functioning like lists. So for instance, for the keys, the keys do not support indexing. However, the values also don't support indexing. Kind of surprising, but nonetheless, they are iterables. You can iterate over them. For instance, for key in me_dict.keys, print key. And I could do this with the values or the items. Note that if we just iterate over a dictionary without calling any methods, it will return the keys as we iterate over that dictionary. We'll talk more about iteration later. As mentioned in a previous video, I believe on sets, we can easily transform data structures into other data structures so long as they have, sort of a similar structure, even if they have different properties. So we've seen we can take a list and turn it into a tuple, or a tuple into a set into a list, or any direction we please. But be aware that as we make these transformations, we enforce the properties of each data structure we pass through. So when we transform a tuple into a set, any duplicate entries, such as the letter A, will be removed. And when we turn the set back into a list, that list still only has a single A in it. As we've talked about dictionaries and sets, we've talked about hashing, and we've talked about how it's very easy to find data in the data structure. This process is referred to as search, and often it's the case that we'll need to know whether or not a particular thing is in our data structure. For instance, if I am running, again, a online store, and users are buying items from me, customers, I might ask them to make a customer account. But I don't want them to make a new account if they already have one. So I might need to search in whatever data structure I have for managing user accounts to see if that user already exists. In Python, we can search data structures using the in keyword. So in my example list, I can check if A is in the example list. And it is, so that expression returns true. However, the letter C, we can see, is not in the list. So C in example list returns false. With a dictionary, we search by key, so we can check if a key is in the dictionary. However, we cannot search the values unless we use the values method to retrieve the values from the dictionary. So, for instance, the key hair is in the dictionary. There is no key has cat in the dictionary. While brown is in the dictionary, it's in the dictionary as values, and therefore, when we search for brown in the dictionary, we are returned false because brown is not a key. However, if we were to search brown in me dict.values, that would return true because brown is in the values. Searching for if an element is already in the dictionary or a key is already in the dictionary can be useful to prevent that key error that we saw before. For example, if we try to access me dict at has cat, we encounter a key error because there's no has cat key in the dictionary. However, we could protect against this error by first checking if the key exists. So if has dog is in the dictionary, we'll print out the results of accessing the dictionary at that key. If has cat is in the dictionary, we'll print out what the cat is, true or false. However, if either of these conditions are not met, we'll print nothing at all. We can see has dog printed out true, while the lines of code checking if has cat exist, we printed out none. We avoided the key error by first checking if has cat was in the dict before we tried to access the dict at has cat. Dictionaries also have a get method that we can use for the same results. I can print out has dog and use me dict.get has dog to retrieve the value at the has dog key. Similarly, I could do this for has cat. In neither case does this result in an error. Me dict.get has cat simply returns none. We could also specify a default value to return if the key doesn't exist. So we could set if has cat is not in the dictionary, we'll return false instead of none. So we'll assume if has cat is not in the dictionary, that's because I don't have a cat, and we'll return false. As we've gone through these operations, you might have noticed that it's very easy to interact with the dictionary based on its keys, but not based on its values. Again, it's useful to think of an analogy to a dictionary of words. When using a dictionary for a language, it's very easy to find information based on the word, and then we can easily get the definition for that word. So if someone uses a word that I don't know the meaning of, I can very easily look up the definition based on the word. However, if I remember some definition, I'm trying to say something, but I can't remember what word expresses that idea, it's very difficult for me to use a dictionary to find the word. I can't find the word based on the definition. Dictionaries are organized in the same way. It's very easy to look up information based on the keys, but not easy to look up information based on the values. In a previous lecture on lists, I had mentioned that one mutation we could make for lists was to sort it using its sort method. How then can we sort other data structures like tuples, which are immutable, or sets or dictionaries, which are not ordered? For this, Python has a sorted function that can return a sorted copy of our data structure. It does not mutate the original data structure, but instead returns a sorted copy. Here, we sort a variety of data structures, including a tuple and a set, and me_dict.items, as well as just me_dict. The tuple and there's a little bit of extra code here where I've mapped string onto the tuple and the set. All that's going on here is I'm converting all the elements of these data structures into strings so that it's easier to assess whether or not the data structure has been accurately sorted. So here we see the tuple in sorted order. It returned a list rather than a tuple, but it's a copy. It's a copy of the original tuple. And numbers come before letters. Capital letters, I guess, come before lowercase letters. And so we have 1, then 2, then capital T, then lowercase a, then lowercase b. And likewise for the set with the duplicates removed. When we sort me_dict.items, we get back our key value pairs, that list of tuples we had before, and we see that they are sorted in order by the keys, the first element of the tuple. Sorting me_dict returns a list of sorted keys. Note sorted also has a keyword. So if I were to sort me_dict items, I could specify that I wanted, instead of being sorted by the key, I wanted it sorted by the value. Since the value is the second element of the tuple, in our key, we'll choose to sort by key value pair indexed at 1, the second element of the tuple. Yes. Okay. So I need here to do a little bit of tomfoolery. Sorry, I'm converting all the values to strings so that we can compare them in order to put them in sorted order. And I've forgotten a parenthesis here. K is not defined. KV0, KV1. There we go. So now the items of the dictionary are not sorted by alphabetical order of the keys, but rather by alphabetical order of the values. I've used something called a lambda function here. I'm not going to discuss lambda functions at this point. They're also known as anonymous functions. We'll discuss lambda functions in a future lecture. We've already seen some examples of iterating over data structures. We've seen when we iterate over a dictionary, we iterate over its keys. But we can also iterate over its values by calling the values method. One of the most common ways to iterate over a dictionary is to iterate over its items, because usually we're interested in the key value pairs. And when we're iterating over the items, it's also very common to use tuple unpacking in the for loop so we can work with the keys and values independently in the body of the for loop. So you'll often see something like this where we're unpacking the key and the value as we iterate through the items. Remember, medict.items looks like, whoops. medict.items looks like this, a list of key value pairs. As our iteration steps through the list, we first iterate onto this key value pair. We then use tuple unpacking to unpack the first piece of the tuple into the variable k, and the second piece into the variable v. Then, after we perform the body of the loop, we advance to the next tuple and unpack that one as well. This is a very commonplace and useful pattern that we'll see again and again. In my lectures on the program flow notebook, I mentioned that there is a special syntax for combining iteration with creation of data structures called comprehensions. Essentially, we use a for loop wrapped within the brackets that are appropriate for creating a particular data structure. So we can have list comprehensions contained in square brackets, or dictionary comprehensions contained in curly brackets, or set comprehensions also contained in curly brackets, but without the key value pair structure. Comprehensions are especially useful when we're transforming one data structure, like a range, into another one, like a list. Here, we compute the squares of the first 10 numbers from 0 through 9 by looping through the numbers in range 10 and returning x squared for each number in that range. As we do so, we construct a list using these square brackets. We can extend this idea to a square lookup table by creating a dictionary instead of a list, where we return a key value pair where x is the key and x squared is the value for each x in range 10. Another advantage of comprehensions is it brings the code closer to plain language, a plain language statement of what's going on. In order to do something like the first line with a regular for loop, we would first have to create an empty list called squares, and then say for x in range 10, squares.append x squared. This gives the same result. However, when we're looking at the code, we have to think a little bit harder about what's going on. We make an empty list called squares. I don't know yet what's going to go into this list, but I imagine it's going to be the square of some numbers. Then, in the next line, we're iterating for x in range 10. It's not immediately clear that this line is related to the line above. It's not until we read the line in the body of the for loop, squares.append x squared, that it's clear what the connection between these two lines is. And cognitively, in our minds, we have to jump back and forth between different ideas about data structures and iteration before realizing the full picture of what this code does. Compared to comprehensions, where we create a variable called squares, which is going to be a list, and the contents of that list will be x squared for every x in range of 10. So I can read this all in one line from beginning to end and get a very clear idea of what's happening in this line of code. Comprehensions are very useful for making your code more readable as long as you are doing a simple, single iterative task. It's not useful for complex tasks where the code starts to get difficult to parse and unreadable. Let's look at some more examples of comprehensions. Here, we can use a dictionary comprehension to transform one dictionary into another dictionary. Imagine that we might need to know what type of data is associated with the keys in me dict. For instance, we might be constructing a database in which we will store user data, and we need to know the data types of the various properties of the users that we're going to put into our database. We can iterate over the items of the dictionary and create a new dictionary with the same keys but with values equal to the type of the values in the original dictionary. So, me dict data types equals a new dictionary with keys k and values type v for each key and value in me dict items. In addition to the data structures actually, I'm going to stop the video here. We'll have one more lecture video about some additional data structures that are introduced by a library called collections.